In the previous video, we discussed how pupil constriction can be used as a behavioral response to measure sensitivity to light. In this section, we will demonstrate an example experiment to test the effects of light with various intensities on the pupil of an individual. In the first example, we are going to expose an individual to a 450 nanometer light pulse with an intensity of 10.3 log photon flux. This wavelength of light is visually perceived as blue light. To figure out about how much the pupil constricted, let's compare this pupil to the pupil constriction scale shown before. We find that the pupil constricted about 68%. Now, if we use a light pulse of the same wavelength, but with the 5 times higher intensity of 11 log photon flux, we can see that the pupil constricts 96%, more than it did with a 10.3 log photon flux light pulse. Similarly, when we repeat the 450 nanometer light pulse, but use an intensity of 10 log photon flux, which is half of the first light pulse, we get a pupil constriction of 44%, which is a lower degree of pupil constriction than at higher intensities. By trying a couple more intensities, we can learn about the effects of different intensities of 450 nanometer light on the magnitude of pupil constriction. Note that the other factors of the light pulse, like timing, duration, and wavelength, are all identical to the first example. So, we can conclude that the different magnitudes of pupil constriction are caused by different intensities of light.
Based on our data, we can see that lower intensities of 450 nanometer light resulted in a lesser degree of pupil constriction compared to higher intensities of 450 nanometer light. But how do we express this data in a more clear and comprehensible way? To do this, we could plot our data with respect to light intensity on the x-axis with log photon flux. And pupil constriction on the y-axis in percents. We use the log of the photon flux in the x-axis to give us a smooth curve when the data is plotted. So let's go to our first example, which had a light intensity of 10.3 log photon flux, which gave us a pupil constriction of 68%. That would be around right here. Our second example was at a higher light intensity and gave us a pupil constriction of 96%, which is right here. Our third example was of a lower light intensity, gave us a pupil constriction of 44%, which is right here. Now I've only plotted 3 data points here, but in this sort of experiment there will be many more intensities tested. If we were to plot these data points and connect them with a line, it would result in a curve like this. Altogether, this data is known as a Fluence response curve. A Fluence response curve is a graph which plots light intensity on the x-axis, in our case, log photon flux, and a behavioral or physiological response on the y-axis, in our case, pupil constriction in percents. This curve represents many different light intensities of 450 nanometer light. Besides light intensity, no other factors about this light change. This ensures that we can draw accurate conclusions from our data.
If we want to test the effects of a different wavelength at the same variety of intensities, we can repeat the same process as before. For example, we could test the response to a 600 nanometer light pulse, which is visually perceived as orange light, at an intensity of 10.3 log photon flux. We can see that although we use the same light intensity for the 600 nanometer light pulse as we did with the 450 nanometer light pulse, the pupil constricted 32%, which is different from the value from the 450 nanometer light pulse. Just by this measurement, we can see that different wavelengths of light will have different effects on pupil constriction. Yet in order to determine how much they differ, we will need more data. So let's test the other 2 intensities with the 600 nanometer light pulse. At the higher intensity, the pupil constricts 83%, which again is different from that of the 450 nanometer value. At the lower intensity, the pupil constricts 15%, also lower than the 450 nanometer value.
Now, let's build a 600 nanometer Fluence response curve, which visually appears as orange. Once again, we're going to use light intensity and log photon flux on the x-axis, and pupil constriction in our y-axis in percents. So going to our first data point, we had a pupil constriction of 32% at a light intensity of 10.3 log photon flux, which is right here. Our second data point, we had a higher light intensity, which resulted in a pupil constriction of 83%, which is around right here. And our third data point, we had a lower light intensity, which resulted in a pupil constriction of 15%, which is right here. Now, once again, we have only 3 data points plotted here, but in this type of experiment, we would have many more light intensities tested. If we were to plot these points and draw a curve, it would look like this. Now we have a Fluence response curve for 600 nanometer light. Notice how it's shifted to the right compared to our previous curve, but retains a similar shape. We could repeat this process with 500 nanometer light, which is visually perceived as green. It would give us a curve looking like this. The same procedure can be followed for violet light, which is 400 nanometers. These curves emphasize the difference in light sensitivity based on wavelengths. While wavelength changes, the shape remains similar. Each of these curves has an S or sigmoidal shape just shifted to the right or left. This is pretty typical for Fluence response curves. We can also see that in the initial part of each graph, each curve has a pupil constriction of 0%. This is because at this point, light intensity is too low to affect the eye. As we move along the graph, we can see that as light intensity increases, the pupil constricts at an increased rate. In the higher regions of the graph, we can see that the data begins to plateau. At the highest point of each curve, the pupil is considered to be 100% constricted. This means that any additional increases to light intensity no longer have any effect on increasing pupil constriction.
So what are the benefits of presenting data as a Fluence response curve? Well, we can see that a lot of data were needed in order to get these graphs. Any number of wavelengths could be tested, and any specific wavelength of light could be tested for a wide variety of light intensities. By plotting our raw data in a clean and comprehensible way, we can more easily see trends in our experiment. For example, we can see that an increase in pupil constriction corresponds to an increase in light intensity. Something important to remember within one Fluence response curve is that the critical factor is the intensity of light. Within any single Fluence response curve, all other factors, including wavelength, are identical between all light pulses.